In this video, we are going to examine a profoundly useful notion for vectors, the dot product. Why do we want to know about dot products? Well, the dot product is going to be a quantity that connects our vectors to geometry. In particular, a dot product is going to measure how much two vectors are pointing in the same direction. We'll be able to use them then to find angles, to find work, and to find projections of one vector onto another. Some things to keep in mind when working with dot products is that when the dot product is positive, it tells us that the vectors are pointing generally in the same direction. What this means is that we know that the angle between the two vectors is smaller than pi over 2 radians or 90 degrees. If the dot product is 0, then the angle between the two vectors is exactly 90 degrees or pi over 2, and the vectors are perpendicular. If the vectors have a negative dot product, then we know that they're pointing generally in opposite directions and that the angle between them is greater than 90 or greater than pi over 2 radians. We have two ways to compute a dot product. The first is algebraic. If we have vectors in 2 dimensions, then v dot w is just going to be v1 w1 plus v2 w2, where v1, v2 are the coordinates of the vector v, and w1 and w2 are the components of vector w. If we expand that to 3 dimensions, we're going to add on a third term, v3 times w3. So in other words, to compute a dot product algebraically, we just take the sum of the products of the corresponding components. A more geometric definition of the dot product incorporates the angle between our two vectors so that v dot w is going to be the magnitude of v times the magnitude of w times the cosine of theta, where theta is the angle between those two. Rearranging that definition gives us a nice way to find the angle between vectors because we can see that the cosine of that angle must be equal to v dot w divided by the magnitude of v times the magnitude of w, and we know we can use the components only of v and w to compute both its dot product and their magnitudes. Let's try a few examples. Here we have two vectors both in 2 dimensions, and we want to compute the dot product between them. V dot w is going to be 2 times 3 plus negative 1 times 4, which is 6 minus 4, which is 2. And so we know then that because these have a positive dot product, that they are pointing generally in the same direction. If we were to draw a picture of the two vectors, 2, negative 1, looks like this, and 3, 4, something like this. And so we can see that while they're certainly not pointing in the exact same direction, the angle between them is smaller than pi over 2 or 90 degrees, and they are heading off at least generally both towards the right. In this example, we have two 3-dimensional vectors, and we want to compute the angle between them and compute the dot product. Well, we can use the component form of the dot product and then use that to find the angle. So we're going to go in that direction. We're going to do the dot product first. So our dot product v dot w is going to be 1 times 2 plus 2 times 0 plus 2 times negative 1. And that is 2 minus 2, which is 0. Well, now we don't even need to use geometry or trigonometry to calculate the angle because this tells us that these vectors are perpendicular, which means that theta is equal to pi over 2, or 90 degrees if you want to write it in degrees, but they are perpendicular to one another, so the angle between them is pi over 2, and of course the cosine of pi over 2 is 0, which would be equal to v dot w divided by the magnitude of v times the magnitude of w, because v dot w is 0. All right, in this last one, we're asked to figure out if the vector v equals 5, 2 is perpendicular to the vector negative 2, 5. So we're going to look at, let's call this one w, just for the sake of simplicity. v dot w is going to be 5 times negative 2 plus 2 times 5, which is 0. So yes, they are perpendicular. Now, I want to relate this back to an idea that should be familiar to you from geometry. I'm going to draw the vector 5, 2. So that vector looks like this, 5, 2. And then I'm going to draw the vector -2, 5. That looks like this. Now, if I think of these two vectors, if I think of them in terms of lines, this line here has a slope. The slope is change in y over change in x. So it went up 2 and we went over 5. This one has a slope. Here we went up 5 and left 2, so -5/2. And if you remember from geometry or from algebra, the slopes of perpendicular lines are negative reciprocals. And it's that negative reciprocal quantity, when we think about the relationship between the lines and vectors that follow those lines, it's that negative reciprocal quantity that forces the dot product to be equal to 0. All right, wrapping up what we know here. The dot product is going to link vectors to the angles between them. We know that a 0 dot product gives us perpendicular vectors. We have both an algebraic and a geometric view or formula for the dot product. We're going to need both of those for various applications. And so what we're going to see coming up soon is that dot products are going to power what we call projections of one vector onto another, and they're going to be very useful in computing work in various physical applications.